Everyone, so now what we want to talk about is this idea of power. And what power is the amount of work that you can do in some unit time. To calculate power, you're going to take the derivative of the work and divide it by time. In order to do that, what you'll get is a watt of power. And you've heard of watts before in terms of light bulbs, possibly. What it means is that for every 1 watt, you have 1 joule of energy you're using every single second. And at the time, James Watt was the one that came up with this idea of machines being more powerful than what was actually pulling things. If you go back to James Watt's time, the things that moved heavy objects for you were horses. So he wanted to see if his engine was as powerful as a horse. A horse was able to lift about a 75 kilogram object up 1 meter in 1 second. That should generate 746 watts. So that's how you get that equivalence down there for 1 horsepower. Another thing you can do is do force times velocity, or force dotted with velocity will also give you a scalar quantity of power in watts. And I'll show you how we can do that derivation right now. Power is work over time. Work, we know, is force dotted with displacement. We're going to divide that by our time factor. Well, if I just look at this in terms of units, I've got newtons times meters over seconds. A newton meter is a joule, so a joule per second is a watt. So that's one way we can do that. But if you look right here, or in the power equation, you can see change in position over time. And we know change in position over time is just velocity. So another way to do the power equation is do the force, the net force, multiplied by the velocity. And when you do it that way, you want to make sure that we assume the velocity is constant as you pull something up. So if I look at the units there for force times velocity, well, force we measure in newtons, velocity is in meters per second, and that looks identical to what we have right up here, so we still get a watt. So you can do force times velocity, or you can do force times distance all over time. And that's how we measure power in watts. So to do an example here, you've got a truck that's being lifted up by a crane. It's pulled up with an upward force of 35 kilonewtons, up with total displacement of about 2 meters. So if you look at this, the object is at rest and is being lifted up by the truck. If I want to calculate the work done by the truck, work is going to be the applied force multiplied by the displacement. The applied force is 35 kilonewtons multiplied by 2 meters. It's going to give me 70 kilojoules. That's the work done by the crane. If we look at the work done by gravity, gravity is a downward force with an upward displacement here, gives us negative work done by gravity. Gravity is pulling down on the truck with 3,000 times g, or about 30,000 newtons down, and it's also going upwards 2 meters. So if you look at that, the gravity is having negative 60 kilojoules of work done against it as that object's raised in the air. The net work done here is the combination of the crane's work plus the gravity's work. So we get about 10 kilojoules of energy or work done on the truck. And if the truck starts from rest, if I know the net work is positive, I know that my change in kinetic energy must be positive as well. My net work here is about 10 kilojoules. I can set that equal to 1/2 mv squared and solve for the speed of the truck once it's moving upwards after this displacement. If I want to know the power associated with the crane, how powerful of a crane I need, let's say it lifted up those 2 meters in about 10 seconds. Power in the crane would be equal to the work done by the crane divided by the time that it takes. The work was 70 kilojoules over 10 seconds, so it's going to be 7 kilowatts of power. That's what that rating must be. If it's 7,000 watts for the motor can handle and lift the truck up the distance that you're curious about. If it's not that powerful, it's going to take longer for that crane to actually lift the truck. Now, since power is joules per second, that's energy over time, if I wanted to solve for the energy that was used, or the work done, you can just rearrange that and get power times time equals the energy or the work done. Because a watt, remember, is a joule per second, time is in seconds, and so in the end, your energy would just be measured in joules. And we talked about if the network is 0, then there is no change in kinetic energy. We also showed that if there was positive work done, our kinetic energy is going to increase, and if there's negative work done, we're going to lose kinetic energy. And one last thing I want to do here is this idea of ratios. And I know some of the problems are starting to ask you more about what if you compare this velocity to that velocity, how does the energy change? And they're not giving you any numbers. And you don't need numbers. When we've got equations are guides to thinking. So we don't have to worry about the numbers that are involved as long as we pull out everything that makes that equation what it is. The example I'll give you here is the kinetic energy. If the kinetic energy is 1/2 mv squared, and an example problem says, what if I double my velocity? What's going to happen to my kinetic energy? Well, if I gave you a mass and I gave you a speed, I'm sure you could tell me my original kinetic energy. And then you would take that velocity and double it, crunch all your numbers again, and get a new kinetic energy and see how much bigger that new kinetic energy versus the old kinetic energy. But you can simply do this with ratios. I said let's double the velocity. So that means in this velocity right here, I'm going to multiply that by 2. So 2 times velocity is what I'm asking. If I double the speed, what happens to k? Well, what you need to do is pull out everything that's in that formula. What makes that formula kinetic energy is the 1/2, a mass, and a v squared. What you leave behind is that 2 inside that bracket, but that 2, remember, is squared as well. If you look here, I've got 1/2 mv squared, and I'm going to multiply that quantity by 2 squared. So 1/2 mv squared is my original kinetic energy. My new kinetic energy, with the speed being doubled, must be 4 times greater. And that's all you have to do when you play with ratios. So we could ask you, what happens in this case if I triple the velocity and cut the mass by 1/3? In my formula, I want to divide mass by 3, but I want to triple my speed. Again, you want to pull out everything that is a constant there. There always has to be a 1/2, a mass, and a velocity. But what's left behind in terms of numbers is a 3 in the denominator and a 3 squared in the numerator. So 3 squared is 9, 9 over 3 is 3. So my new kinetic energy is now 3 times more than it used to be. And I didn't have to worry about what the mass was or what the actual initial speed was. I just know that if I change those factors, I can change my kinetic energy. Think about it in terms of the spring constant. Work done by a spring, we said, was 1/2 kx squared. So the same thing can apply here. What happens if you pull the spring 3 times further? Do that example and show me that you know how to do this ratio. You should end up with the work in the spring being 9 times greater. Or the example we did at the end of class today with the spring doing work on the block and making the block move. We saw that the work done by the spring was a positive amount of work, and if there was positive net work done, that means our kinetic energy changed from its final state to its initial state. The final state being something with velocity and the initial state being 0. So we set up this formula and said 1/2 kx squared equals 1/2 mv squared. Things that we didn't need. We didn't need these 1/2s because they're on both sides. So if I wanted to solve for v, v is equal to the square root of kx squared over m. And we could say, well, how do we increase the velocity? To increase the velocity of that box, I needed to decrease the mass, so cut it in half. Or I could increase the k constant. Or I could stretch the spring even further. So if I do those 3 things all at once, I can tell you what the new speed is without even having to punch in any numbers. X is squared, so the stretch was squared, so 2 squared is 4. The spring constant got 4 times bigger, so 4 times 4 gives you a 16 on top, all over 1/2 in the bottom. So really what I'm left with is a square root of 32 multiplied by everything else that's underneath that equation. So the velocity is increasing by the square root of 32 times faster than it originally was. And that's how we can use ratios. One last example I'll do with the ratios is going back to centripetal accelerations. We said that for centripetal acceleration, it was v squared over r. The question was posed to you then, what happens if you increase your speed or decrease your radius? At v, or the centripetal acceleration was 1g. Question could be, how could we make that acceleration bigger? How could we make it 4g? Well, one thing you could do, decrease that radius by a quarter. You cut that radius down by 4, that 4 has to go up top, and you'll get 4 times the acceleration. Or, instead of making a really, really sharp turn, just make that turn at twice the original speed. If you do it at twice the original speed, 2 squared is 4, and I get 4 times the centripetal acceleration. So as long as you do the same thing to one side, you can do it to the other side and use ratios to solve your problem.